In this video, we will learn about structural isomerism. We will define and identify the three types of structural isomers, learn why it is important to distinguish between different isomers, and deduce and name possible isomers from a given molecular formula. Imagine that you are working in a lab and you need a compound that contains 5 carbon atoms and 12 hydrogen atoms. So you head off to the stockroom to find your compound. You were surprised to find 3 different bottles that are all labeled C5H12, but each has a different chemical structure. And indeed, they each have 5 carbon atoms and 12 hydrogen atoms. Each of these structures represents a structural isomer of C5H12. Structural isomers are compounds that have the same molecular formula but differ in the sequence in which the atoms are connected. More specifically, the 3 structural isomers of C5H12 pentane are chain isomers, a subset of structural isomers. Chain isomers differ in their carbon chain arrangements. There are 2 other types of structural isomers, positional isomers and functional isomers. Positional isomers differ in the position of their functional group, and functional isomers have different functional groups altogether. It is important that scientists recognize that many isomers can exist for a given molecular formula, as each isomer will behave differently. When comparing chain isomers, straight chain alkanes can pack more tightly with one another, allowing for greater intermolecular forces between the molecules. As such, straight chain alkanes have higher melting and boiling points than their branched isomers. The position of a functional group can also change the reactivity of the isomer. And changing the functional group altogether will change the properties of the compound and its reactivity. Choosing the appropriate isomer is important to ensuring a safe and effective reaction. But if all isomers have the same molecular formula, how are we able to tell them apart? Learning to name various organic isomers will allow us to distinguish between them. We will focus here on naming simple alkanes, or compounds which only contain single-bonded carbon atoms. The first step in naming alkanes is to recognize a compound's base chain. A base chain is the longest continuous chain of carbon atoms in the molecule. This molecule shown below only contains one carbon atom, or a base chain of 1. It is given the name methane. The prefix meth indicates the carbon length, 1 carbon, while the suffix ane indicates the primary functional group, in this case an alkane, single-bonded carbons. As the chain length increases, the suffix ane remains as the functional group stays the same, but the prefix for the length will change. Eth for 2 carbons, prop for 3, but for 4, pent for 5, and so on. We encounter some difficulty in naming when the compound is not a straight chain or has branches. This compound contains 5 carbons, but it doesn't look like pentane, a straight chain. To name this isomer of straight chain pentane, we will perform the following steps. Step 1. Identify the base chain and name it appropriately. The base chain is the longest continuous chain of carbon atoms in the structure. In this case, the longest continuous chain of carbon atoms is 4. A 4-carbon chain is called butane. But for 4 carbon atoms, and ane representing single-bonded carbons. Step 2. Number each carbon of the base chain so that the branches, or substituents, appear on the lowest possible numbers. When comparing a series of values, choose the series with the lowest number at the first point of difference. To number the base chain, I will start at the leftmost carbon and number across, 1, 2, 3, 4. Then I will repeat this process starting at the rightmost carbon and number across, 1, 2, 3, 4. I will then compare the values for the substituent represented here in green. It is attached at the second position if I count from left to right, and the third position if I count from right to left. I will choose the lower of the two options. Step 3. Name the carbon substituents in the following format: a position number, dash, the appropriate length prefix, dash, and YL used to indicate that this piece of the molecule is a substituent. The substituent has only one carbon atom. Be careful to never recount carbon atoms that are part of the base chain. We will therefore name this substituent 2 for the position on the base chain, meth for one carbon atom, and il, so 2-methyl. If the molecule had more than one substituent, we would proceed with steps 4 and step 5. As this compound has only one substituent, we will skip these steps for now. Step 6. Place the base chain name at the end of the substituent or substituent list if more than one. This is the final isomer name, 2-methylbutane. Let's examine these steps again with a slightly larger structure. Step 1. Identify the base chain and name. The longest continuous chain of carbons in this structure is 6, so the base chain is called hexane. In step 2, we will number the base chain from left to right and from right to left and compare. The substituents appear on carbon atoms 3 and 4 regardless of the direction used. However, if we count from left to right, we will see that there are 2 single carbon groups on position number 3. Each will be assigned its own value, so we list the 3 position twice, followed by a 4 for the second carbon group. If we count from right to left, we will see that there is a single 2-carbon substituent on position number 3, followed by 2 substituents on position number 4. We will choose the series of values with the lowest number at the first point of difference. Both lists begin with a 3, but the leftmost list has a 3 as the second value as well. As this is lower, we will choose to count from left to right. Then, we will name each substituent in the following format. There are 2 methyl groups at position number 3, so we will list them both separately, and an ethyl, 2 carbons, at position number 4. Since there are more than one substituent, we will proceed with steps 4 and 5. Step 4. If more than one substituent, list them in alpha order with dashes in between. We will put the ethyl first, followed by both methyl groups. Step 5. If any of the substituents are the same, list all position numbers separated by commas, followed by a prefix for the number of substituents, followed by the substituent name. We have 2 methyl groups. These will be combined in our list. We will list each number separately by commas, followed by di representing the 2 methyl groups, and finally the word methyl. Notice that our names, ethyl and dimethyl, are no longer in alpha order. It is always helpful to put the substituents in alpha order before combining like terms, as the prefixes di, tri, and tetra are not used when determining the naming order. Finally, in step 6, we will add the base chain name to the substituent list, or 4-ethyl 3,3-dimethylhexane. Naming isomers allows us to easily distinguish between them. If we do not know which structural isomers are available, we can also determine their structures. A good first step for drawing any organic structure is to calculate the degrees of unsaturation, sometimes referred to as the index of hydrogen deficiency. A degree of unsaturation of 0 will indicate that all of the isomers of that structure will not contain rings, double bonds, or triple bonds. Double bonds and rings will each require 1 degree of unsaturation, and triple bonds will require 2 degrees of unsaturation. Calculating the degrees of unsaturation will provide insight into how to draw out the structures. The equation for degrees of unsaturation is as follows: 2 times the number of carbon atoms plus 2 plus the number of nitrogen atoms minus the number of hydrogen atoms minus the number of halogen atoms, all divided by 2. For example, we can calculate the degrees of unsaturation for C6H14. 2 times 6, the number of carbon atoms, plus 2, plus 0 nitrogen atoms, minus 14 hydrogen atoms, minus 0 halogen atoms divided by 2. This gives us an answer of 0, indicating that all isomers with this molecular formula only contain single bonds. Using this information, we can attempt to draw all of the structural isomers of C6H14. Since only single bonds are used, we can begin by drawing the simplest base chain, hexane. From here, imagine that one carbon atom is removed from the end of the chain and added as a branch elsewhere in the molecule. We do not want to add this carbon at position number 1, as this would give us 6 carbons in a straight chain again. So we will start by adding the carbon at position number 2. We can also try other positions on this chain. And this is where we need to be careful. If we look at the second and fourth structures, these structures are in fact identical. This may be difficult to see at first, but if we name them, we find that they are both named 2-methylpentane. Therefore, the bottom structure is not a new isomer, but a duplicate of an isomer we have already drawn. We have moved a single carbon to every new position in the structure. So let's imagine that 2 carbon atoms are removed from the original straight chain hexane. This leaves a 4-carbon base chain with 2 possible attachments, either 2 methyl groups or 1 ethyl group. We will start with the methyl groups. Both methyl groups could be attached at the same carbon. Remember, adding groups to the first or last carbon in a base chain will lengthen the base chain, resulting in structures that have already been drawn. We could try moving both methyl groups to the next carbon. Notice that once again, these are the same structure. If we rotate the structure on the right, it will look identical to the structure on the left. We can also separate the methyl groups to create a new isomer. Finally, let's try a 4-carbon chain with an ethyl substituent. This is in fact identical to a structure that was already drawn. If we identify the base chain, we should see that the base chain is now 5 carbon atoms long, and that both of these structures, when named, are 3-methylpentane. As an important rule, if the substituent is longer than either side of the base chain it is attached to, adding the substituent will lengthen the base chain. Here, the ethyl group that we added was longer than the methyl group to its left. Its addition changed the base chain from butane to pentane. Here are the 5 structural isomers that we identified for hexane. Let's repeat this process to determine how many isomers there are of C7H16. We will start with the simplest base chain, heptane. From here, we will remove 1 carbon from the end, leaving a hexane base chain and a methyl substituent that we can move along the chain. Starting on position number 2, we place the methyl group. It may be helpful to number your base chain in both directions to see which positions are the same. We move the methyl group along the chain to create new isomers. Be careful to notice when the methyl positions are the same, as this will not be a new isomer. When all position options have been exhausted, return to the heptane and remove 2 carbons from the chain. This leaves a pentane base chain with 2 options for substituents, 2 methyl groups or 1 ethyl group. We will start with the methyl groups on the same position. When the methyl groups cannot be moved to a new carbon atom in the chain without creating a duplicate, separate the methyl groups. Once the methyl options are exhausted, we move to the ethyl. Notice that if the ethyl group is added to the second carbon atom in the pentane chain, it will lengthen the base chain. The ethyl can only be added to the third carbon atom on a pentane base chain. We can then attempt a butane base chain with 3 methyl groups. We know from the isomers of hexane that we cannot add any group larger than a methyl without affecting the base chain length. We position the methyl groups in the only arrangement possible and discover that there are 9 isomers of heptane. Let's review the key points. Structural isomers have the same molecular formula but different sequence of atoms. There are 3 types of structural isomers: chain isomers that differ in carbon chain arrangements, positional isomers that differ in functional group position, and functional isomers that have different functional groups altogether. Structural isomers have different properties, with straight chain isomers having higher melting and boiling points than their branched counterparts due to increased intermolecular forces. And isomers have the same molecular formula but different chemical names, which allows us to distinguish between them.